this matrix. But if you put a 2 there, it's nice, because if you tilt your head and squint, you can see that this is really nothing more than x comma y as a row vector times the vector matrix A, B, B, C, times x, y. And this is the so-called matrix of the form. Matrix of Q. So you may or may not be familiar with matrix multiplication. We can talk about it sometime if you're not. It's not really a big deal. Bottom line is there's just like super slick formula for a quadratic form. It looks like this. Q of V is equal to V transpose matrix of Q times V. So let's call that matrix big A. Now once you know that you can write a quadratic form as a matrix multiplication of vectors sandwiched between, and then you can prove stuff about quadratic forms like pretty fast. For example, what if you take and you scalar multiply x and y both by the same number? So that's like C times V. What does that give you? CV transpose times A times CV. Properties of matrix multiplication. If I've got a number, it just pulls out. So I get C squared V transpose A V, but that's C squared times Q of V. So if you multiply both of the inputs by a number, it pulls out the square of the number. The other thing, the other property, slightly less trivial, but I believe I can explain it to you a lot faster than Stillwell, because he does not embrace linear algebra as I do. I mean, that's fine. This is property. Any questions? I mean, again, if you're not comfortable with matrix multiplication, do not despair. Talk to me about it in office hours. I will explain. Can I erase?
All right.
Here's the other thing I want to prove that's less easy. I'm hoping, though, that it's going to work out. So if we have Q of, say, V plus W plus Q of V minus W, allegedly, all right, that is equal to 2 times Q of V plus Q of W.
Can you change your color?
What's that?
The blue is bad.
This blue is bad, yeah.
Yeah.
You got the rest?
Yeah.
Okay. Why would we care about quadratic forms? I mean, what's Pell's equation? It's x squared minus ny squared, right? It's a quadratic form. So if you can say something general about the possible values a quadratic form takes, that says something about whether or not you actually have solutions corresponding to when that quadratic form attains a certain value, right? In this case, in our case, 1. So how we prove this, I think, could be wrong. It's pretty easy if we just let the matrix multiplication properties do the job for us, basically. So let's see here. So let's try, which side do you guys want to start with? I'm going to start with the, this looks like the harder side. I'm going to start with that side. So Q of V plus W plus Q of V minus W. We'll trade that for a statement about matrix multiplication. That's V plus W transpose times A times V plus W, parentheses, plus V minus W transpose A times V minus W, where A is in the matrix of Q. And then this is multiplied out. I got V transpose AV plus V transpose AW plus W transpose AV plus W transpose AW That's all from just foiling out the first term. By the way, guys, I'm using that V plus W transpose is V transpose plus W transpose. That's how that works. And then foiling out the second term, I get V transpose AB minus V transpose AW minus W transpose AB plus W minus W plus W transpose AW. I think the cross terms cancel. Like this as that is its natural enemy, and likewise this guy gets canceled by that guy. And you're just left with 2 times V transpose AB plus 2 times W transpose AW, which is, of course, 2 times Q of V plus Q of W. And check it out, that's it. I believe this is called the polarization identity for quadratic form, but I could be wrong. So, who cares? I mean, what's the point of this identity? The point of this identity is it links values of the quadratic form, right? It says that if I know how the quadratic form depends on V plus W and V minus W, then that gives me information about the values of the form at V and W respective. So, let's see here. I guess when you take V equals to W, we just get back to the case what? C equals to 2, right? Take V equals to W, you get 4 is the C squared. All right, so then it has something to do with this mysterious picture. I'm going to start to tell you this story today. I'm not going to finish it, but I want us to get started to think about this idea. So one way to think about solving these equations is you really want some way to probe all possible things in the integer lattice, right? So the question is, how do you get all possible integer pairs? Well, there's a simple theorem basically says if you've got a relatively prime pair of integers, if you look at all integer linear combinations of that relatively prime pair, you can reach all points in the integer lattice. It's essentially from more or less from Dessau's identity, and a little bit more than that, but the question is, what are the relatively prime pairs of integers? Well, we talked about the positive ones before when we looked at that tree and you guys had to do the next branch. Here's the next step in that story. What about negative pairs? So the way this works is kind of tricky. So here I have the fundamental pairs, 0, 1, and 1, 0. Those are relatively, well, they're not relatively prime. Everything else is relatively prime. I mean, 0 is there, exceptional case. If you add these two together, right? 1 plus 1, I get 1, 1. On the other hand, if I take the difference, I get minus 1 and I get minus 1 and 1. So we just write it that way, we have convention. So 1 minus 1. And then so if I take, for example, this and this, so 2 minus 1 is 1. No, how am I doing this? Add these guys, and I guess you just add both, right? Duh, yeah, so 3 minus 2, and let's see, to get from here to here, I'm also adding. Why do I have different numbers? I'm sorry, I'm confused also.
You add the negative 1 with the 1, 0 to get the 2, negative 1. Oh, I mean, that's how it.
Yeah.
And then 1, negative 1 plus 1, 0 gets you 3, negative 1.
So you.
Oh, I mean 2, negative 1 plus 1, 0 gets 3, negative 1.
So he adds the plus with a plus to go right?
To go left. I don't know.
I mean, to go from here to here, he's adding the plus with a plus, right?
Yeah.
To go from here to here, he's doing what? He's
The difference between 1, 0 and 0, 1.
Use the 1,
he's
0
adding the plus on
minus
the
0.
bottom to the minus on the top, right?
Mm-hmm.
Is it that again down here? The plus on the bottom to the minus on the top. So minus gives me, no, it's not that.
You have to add them to get those
Add
numbers.
1 minus 1 with 1, 0.
Yeah.
At the
1
bottom
minus-
1.
Yeah.
you use plus minus 1 minus 1 plus the plus minus 1 0. So you have 2 negative 1.
So how do you explain this 3, 2 here?
So you would do 2 negative 1 plus 1 minus 1.
Yeah.
Okay.
When you go up there, you have to take the difference.
So the point here, though, is if you think about this, you can reach all possible v1 and v2 that are integers by adding relatively prime pairs. So this tree has basically like this list of possible fundamental ingredients for the integer lattice. So if you can see what a given quadratic form does on this tree, then that tells you what the quadratic form does everywhere. And that's why he has this picture. So what he's doing is he's looking at the quadratic form x minus 3y squared, which corresponds to Pell's n equals 3 equation, right? And you see solutions to Pell's equation popping up here, here. Oh, that's all for this picture. But in the circles are the values of the quadratic form. These are, and so like, those are the only values which it can pick up. And so you can, by looking at this paired with this identity, you can then figure out what are all the possible values the quadratic form takes over the integer lattice. Here's more of it. So if you keep going on this tree of integral bases formed by adding the numbers, and the plus minus doesn't really matter because of the identity I erased over there, but there's the Pell equation for n equals 3 solutions. There's the 1, 0, which is the identity solution, right? 2, 1, the fundamental solution you guys guessed for me. Here's the one we built by the square of the fundamental. 26, 15, here's the one we discovered as a cube of the fundamental. But you see these are appearing, they're appearing as the values that are going in this tree of integral bases. So you're seeing the solutions pop up. And also the solutions to Pell's equation happen to fall on this thing called the river. What's the river? There's some divided, so if you draw the whole tree and you look at the values of a given quadratic form on the tree, there's going to be some dividing line where above that line you have positive solutions and below that line you have negative solutions. He actually has a proof that there exists this so-called river, right? Now, this part of the book is what makes this book special and is why like a lot of advanced schools are using Stillwell for their number theory, their graduate number theory course. They actually get into this cover. It's homework. I don't in here because this is complicated. But as I was telling Troy, if you could figure out how to like make an app for that, like, because it's fairly clear. I give you a quadratic form, you look at the tree of integral bases, you find the river, and then just like plot it. And I mean, I asked the internets if it was a known thing, but apparently no one's done it nicely yet. But it's something you can clearly implement if you were more adaptive programming than I am. And of course, it's interesting because I think you'll be able to find the fundamental solution to Pell's equation as you travel the river. Right? It has to be below the river. The first thing past the identity is the fundamental solution. I think that's a general description. So, but I don't know. I mean, what does that look like for that one we saw with those awful numbers? I have no idea. Anyway, I've shown you what I can understand about chapter 5. I'm sorry if there's many things I don't understand. You can, of course, ask me questions. Now for the test, guys, which is when? Tuesday. Hope springs eternal now. Tuesday. What are likely questions for the test? You guys have any ideas? Emissions? Roughly speaking, yeah.
One Chinese remainder.
Will there be Chinese remaindering? Yeah, probably. In the co-prime case, I'll vouch for one of those. We figured out that's not too hard to solve, right? Even if you forget the silly theorem, you can still solve by substitution, right? Linear Diophantine equations, pretty good guess. I probably have you solve one of those. maybe it could even be like solve or say it's not possible to solve it. Explain why. That's a good problem. How about find the binary representation of a given number? That's also a very fair question. Application of Fermat's Little theorem or Euler's theorem, or even Wilson's theorem about the factorial, right? The n factorial is congruent to n minus 1 factorial is congruent to -1, right? That's what we're
Wait, Wilson from what?
Yielders?
Yeah, Euler's. So the application of Euler's theorem in mission 3, calculate 3 to the quadrillion mod something. So you can use the Euler P function of something to chop down the large number. Yeah.
Are we gonna have to know how to decrypt messages using large round methods?
I would like for you to know the general idea of encryption, but I don't think the actual encryption is a reasonable thing for the test because it's too computational. I might ask you some of the calculations that you were asked to do during the decryption. Like I might ask you to take some message M and, raise it to the 52nd power or something, or 532nd power, it doesn't really matter. You should know about the fast binary exponentiation. So let's see, as I think about chapter 4, the encryption chapter, things that pop out to me are proof of the multiplicativity of the Euler phi function, right? The phi of P1, P2 is equal to phi of P1 times phi of P2. Like, it'd be good if you knew that. It'd be better if you could prove it. Remember the one I got confused about, but we decided my proof that I already wrote was right. That one. And the other thing, of course, is the way you use the Euler phi function. The whole mathematical apparatus of the decryption is fine, but I wouldn't ask you for a specific numerical example. The entirety of the message is it's just too awful, right? I was saying something. I still like to know why it always comes back to the same thing again for the example we looked at. Let's figure that out. Make something. Make that a test question. Specifically that, why did our encryption toy example blow up in our face? What happens if I ask that in the test, I wonder?
You're going to use the funny answers. I already tell you the answers.
I agree.
Those of you who know me, is it within my powers to ask this question on the test?
Yeah.
Yes. If I run out of time to write more interesting questions, what would I gravitate towards? That very question. But I'd like to ask a better, more interesting test than that. So, from chapter 1, we covered chapter 1 the first day, right? What's important from there to know about?
Euclid's algorithm.
Yeah, Euclidean algorithm for sure.
Visibility.
I think I inadvertently ruled out proof of the division algorithm on the test by some earlier statement, which I regret, but it is what I said. I fashioned myself in class to be like the Babylonian kings of old, or the Persian kings of old. My word is binding when it comes to things that can't be on the test, and we're stuck with it. So, I don't know, I'm trying to think of, what are the numerical problems we've done? Some modular calculation out the wazoo, right? Like, simplify this mod 15, or simplify this mod 30, those sorts of things, obviously.
Like the least positive residues.
Right. The last 2 problems on mission 3 are bonus. I've not given you the technical prowess that you need to solve those well.
Bonus on the mission or bonus on the
Mission, they're bonus on the mission, and since they're bonus on the mission, that means I don't consider them required for the test. Chinese remainder coprime is fine.
test? Right.
And it's not far from it to solve those last 2 problems, but I have not explained it yet, and it's not still well. So those aren't fair. Unless you have time to check 24 numbers, or 21 numbers, whatever, yeah.
Continued fractions or Egyptian fractions?
Continued fraction, Egyptian fractions, great problems. Those would be ideal test questions, right? Those are relatively present. And of course, I'll probably try to ask you guys some simple proof questions like, here's in one, proof consecutive integers are even, the product of consecutive integers are even, there's a great test question. Or that a times a plus 1 times that mission problem about divisibility by 6, that's a great question. All of those theorems we had about divisibility, great test questions, right? Those are all simple to prove, nice, clean. I can see if you know how to prove things or not. Gives us a chance for you to get better at proving things before you hit the awful monstrosity of Math 421. Oh my goodness, it's the hardest course on earth, right? No, just kidding. Okay. Anyway, that's about all I have. I will search my soul and try to see if I have more to say. I'm working on writing up a large test review which collects all of the major theorems and definitions in one foul odious document, and I will send that to you since I have done. I've got this little thing called the linear test degree though, so I gotta get that done today. Anyway, thanks guys.